Well, good afternoon. This is a video to walk you through the solutions to the midterm number 2 questions. So the first question, you want to see which molecule contains only single bonds. And so let's do the Lewis structure for all of them and then we can see. So we need to know valence electrons. So carbon has 4. If I look at periodic table, carbon has 1, 2, 3, 4 valence. Hydrogen has 1. Okay, so that means we have 4 for the carbon and 4 for the total of all the hydrogens. So that's 8 valence electrons. Oxygen has 6 valence electrons, and then another 2 for the hydrogen, so that is also 8. Oxygen and sulfur are in the same group, so all of those will have 6, and so there's 3 atoms, each with 6, so that's a total of 18 valence electrons. And then oxygen, we said was 6, so that's 12, 13, so that's 14. And then chlorine has 7 valence electrons. So when you have 2 of them, so that's also 14. Okay, so carbon, let's put the hydrogens around. And we see that we've placed 8, all single bonds. Okay, so it can't be that one because we're looking for the exception. So something that has something other than single bonds in this case. Water, we placed 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that also is just single. SO2, if we place 4, and then let's build up around the outside. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, and so for this, sulfur doesn't have an octet. So sulfur can expand its octet, but it can't have less. Okay, so we have to do one of these numbers. Okay, and then we could do the resonance form as well with all the dots. Okay, so now we have something that is a multiple bond. It's something other than a single bond. Okay, just to kind of complete these, H2O2. Okay, we have to place 14 electrons. So far we placed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So no need to use any double bonds. And then Cl2, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So also just a single. Okay? This next one is balancing. So I would do boron first. Then let's do maybe fluorine. So we have 6 over there, so we need a 6 there. And then maybe hydrogens. So you have 6 in the reactant, so we need a 3 there. Okay, and then just double check to make sure oxygen's balanced. And you have 3 and 3. So that is the right answer. HFCs, so this is a definition, so that means you have hydrogens, fluorines, and carbon. Okay, so the only one that has a hydrogen, fluorine, and carbon only is this one, right? This has a chlorine in it. So this is just, I guess this one has a hydrogen, so this would be an HCFC. This, I guess also HCFC. And that one also is a HCFC, because you both have chlorine, fluorine, and carbon. Okay, so this just has a hydrogen, fluorine, and carbon. Okay, so just a definition. How many carbon atoms does octane have? So oct means 8. Why does ozone drop at night? Because we looked at the mechanism for it, and it requires sunlight. Reference to waves, frequency is the number of waves that pass a unit point. Okay, so if you have a fixed point, it's how many waves pass that. Okay, so again, just definition. A wavelength would be this distance. Wave frequency is how many waves are passing a particular point. Which of the following is a resonance structure? Okay, so if we look at SO3, each of those has 6 valence electrons, so you have 4 atoms, so it's going to be 24 valence electrons. This one is similar, except you have another 2 from the charge. That's going to be 26 valence electrons. Iodine is in the group 17, so that's going to have 7. Each of the iodines are going to have 7, so that's 21, and then you have another 1 from the charge, so that's 22. SCO, so you're going to have 6, 4, and then another 6, so that's going to be 16 valence electrons. And then boron has 3 valence electrons. And then fluorine, each of those are 7. So you're going to have 21, and 3 is 24. Okay, so again, you're just counting based on what group they are in the periodic table. And so SO3, if we look at that, we've placed 6, 7, 8, 9, 10, 11, 12, 18, 19, 20, 21, 22, 23, 24. Sulfur doesn't have an octet, so we're going to have to do that. Okay, but then we could have placed it over here or up here. Okay, so this definitely has resonance. Okay, so it's listed as the first answer, so you really didn't need to go any further, but let's just see these others. The difference with this next one, it's also SO3, but now you have 26 valence electrons. So we place 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So now the sulfur is happy. It's got 8. So there's no need to use any multiple bonds. The I3 looks like that. We have to place 22. So sulfur replaced 4, 5, 6, 7, 8, 9, 10, 16, 17, 18, 19, 20, 21, 22. Okay, so again, iodine is one that can expand its octet, so that has more than 8, but it's okay with that. So no need to use any multiple bonds, so there's no resonance forms. SCO, carbon is in the middle. Okay, so we have to place 16, so we place 4, 7, 8, 9, 10, 16. Okay, and then we notice that carbon doesn't have an octet, so you have to do that. It still doesn't, so you have to do it from the other side. Okay, and now there's no need to shift double bonds around. Okay, so no resonance. And then boron trifluoride, we go around. We're placing 24 valence electrons. Boron is one that is an exception in the group 13. So anything in this group, they can have 8, but they are totally happy with less than 8. Okay, and so that is the Lewis structure for there. And again, no need for any resonance. Which of the following has a central atom a formal charge of +2? Okay, so aluminum, its valence, 1, 2, third group from the left. So that would be 3 minus the number of bonds coming from the aluminum is 4, and you don't have any additional dots. So that is a -1 charge. So that's not a +2. Okay, ozone, we have 6 for its valence, so it's the 6th group from the left. And then you have 3 bonds, 1, 2, 3. And then you have 2 dots. Okay, and so that gives you a +1 charge. Again, not a minus, or not a +2. Beryllium, 2nd group from the left, so it's 2 minus 2 bonds and no dots around it, so that's a 0 charge. This sulfur is 6 minus 6 bonds, and again, no dots around it, so that's also a 0 charge. And so by process of elimination, it's really this. And so you see 6 minus 4 bonds, right? 1, 2, 3, 4. Okay, and no dots around the center atom. And so that is a +2. Okay. Increasing wavelength. So remember that as you increase wavelength, you are decreasing the energy. Okay, and so as you go in this direction, that is decreasing energy or increasing wavelength. Okay, so just kind of a definition there. Ozone is important because it absorbs UV, so that was the purpose of that whole chapter, really. Ozone is a secondary pollutant, and so that means it's not produced directly. Okay, so you need sunlight and you need vehicle emissions for you to generate ozone. This one, when we're doing Lewis dot symbols or Lewis structures, the dots mean valence electrons. Okay. So this one, the Lewis structure for CS2, so there each sulfur is 6, and we have 2 of them, so it's 12, and then another 4, so 16 valence electrons. So it plays 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so we have to do that, and we have to do that. So that's the right answer. Okay, this one, oxygen molecule breaks apart at lower wavelengths, so that means higher energy than the ozone. Okay, and so if you look at the Lewis structures for both, that's oxygen, and then remember ozone was this with its resonance form. Okay, so these bonds in ozone are kind of between a single and a double, whereas this in oxygen is a double. And so we would say the average bond in oxygen is shorter and stronger. Okay. This definition, so the air we're breathing is in the troposphere. The stratosphere is above that. The ozone hole is most prominent over Antarctica, okay, and that has to do with these polar stratospheric cloud formation. It's colder in the Antarctic versus the Arctic. Okay, so you get these PSC formation. A balancing question, so I would do aluminum first, then maybe carbon, then let's do hydrogen. So now we've got 12 and 12. Right, so that's, yeah, so that would be a 12 here. Yeah, so that means 24 hydrogens on both sides. Okay, so the 12 is for water. Formal charge on the fluorine in the structure. So let's do its Lewis structure. And so each of these are in group 17, so they have 7 valence. So that would be 21, and then you're taking 1 away, so that's 20 valence electrons. So ClF2, so we place 4, 5, 6, 7, 8, 9, 10, 15, 16, 17, 18, 19, 20. Okay, and so what's the formal charge on the fluorine? It's 7, its valence, minus 1 bond, minus 1, 2, 3, 4, 5, 6 dots. So it's a formal charge of 0. Okay, and we saw this, so as chlorine went up, ozone was going down. Okay, so that was kind of the smoking gun evidence that chlorine was involved in stratospheric ozone depletion. Okay, what's wrong with this Lewis structure? Okay, so if you look through these, hydrogen's happy with 2 electrons. That's cool because that's got an octet. That has an octet. This does not, though. So that's what's wrong with it. Okay. Which groups undergo ionic bonding? So there you need a metal and a non-metal. What has the shortest wavelength? And so it would be, again, the shortest wavelength means the highest energy. So it's going to be the region that's closest to the UV. So that's going to be blue. Okay, so Roy G. Biv. And then, so this is your visible. And then you've got UV on this side and then IR on that side. If we're going from, I guess the way I've got it is kind of weird, but this is like increasing energy here. Okay. The air quality index, what is most hazardous? Remember I said CMU colors, so that would be our maroon. A bounced reaction between nitrogen and oxygen to form NO. Okay, and so remember on the final exam, I may not be nice enough to give you that. So if I just say nitrogen, oxygen, remember that they are diatomic. Okay, and so in this case, to balance it, it's pretty simple. Just put a 2 there. The best Lewis structure for ozone, and we already talked about that one, so that is it. So it's just one of the resonance forms. The other one is where the double bond is there. Which has an atom with an expanded octet. Okay, so I think you can see just by looking at this, you have 5 atoms around a central atom. And so if you look at it, not even getting into like counting valence electrons, you can see that the arsenic has 10 around it, right? 10 electrons. So 2 electrons from each of these bonds, and you have 5 bonds, right? And so that would be expanded. This, which is definitely incorrect. If you're looking again, the one that really stands out is that, because carbon doesn't have an octet. Okay, this is an exception. If you have an odd number, remember we went through that in class. Nitrogen also doesn't have an octet, but it's one of these where, it's an odd number, so you're going to have one atom with just a single dot. So we call this a free radical. Okay, so that is actually fine. So this one is wrong because carbon needs an octet, and so its true structure would be this. Okay, where you have a triple bond. All right. This one, what can you encounter indoors? Carbon monoxide poisoning. Particulate matter, that's soot, for instance. All these others are gases. This one, UVC, is the most energetic. That's correct. And then a calculation. So if we have a wavelength of 580, what is frequency? And so we would use this one. Okay, and then we want to know frequency, so let's just rearrange it. into this. And so we've got 3.0 times 10 to the 8th meters per second. And then we're going to divide by the wavelength, but it's in terms of nanometers. So let's convert it to meters. Okay, so then the meters will cancel. And so we've got 1 meter is 1 times 10 to the 9, a whole bunch of those nanometers. Okay, so that would be 3 times 10 to the 8th. And then on the bottom, we've got 580 divided by 1e to the 9th. So this can simplify to 3.0 times 10 to the 8th divided by 5.8 times 10 to the minus 7. Okay, so if you divide those out, you get 5.17 times 10 to the 14, and the unit here is inverse seconds, or hertz. So these also could be written as hertz. Okay. All right, so I hope that helps clarify things. As always, let me know if you need any additional clarifications. All right, take care.